Hello, in this video we're going to be looking at wave-particle duality and how this relates to atomic emission spectra. So we'll start with just a simple review of what we mean by wave-particle duality. So we know from variety of experiments, interference effects lead us to conclude that light behaves as a wave. But we also know, based on experiments and theoretical developments at the beginning of the 21st century, that light behaves as a particle. There's black body radiation, which is objects glow as they heated and they change colors as they are heated and get hotter. There's something called the photoelectric effect, which is the basis of light sensors. There's something called Compton effect, in which light seems to be able to transfer momentum to particles. And this leads to several equations that are critical to this concept of light behaving as particles. And so, for example, when we talk about particles, of course, we know that we're talking about photons. And the energy of the photon is given by an equation which relates to the frequency of the photon. And also relates to the wavelength of the photon. This is the Greek character lambda. Now, the H is referred to as Planck's constant, and that's given by this very small number here. And C is just the speed of light, which is given by this number here. We're going to need to be able to use these in order to do our calculations associated with the energy of photons as a function of frequency and wavelength. So we also know that if light behaves as a particle, and we thought it was a wave, it certainly exhibits interference effects. Do particles behave as waves under specific circumstances? And so in 1924, Louis de Broglie actually in his PhD thesis came up with this simple equation which related the wavelength of a particle to its momentum. P represents momentum. In classical physics, that momentum is just the mass of the particle times its velocity. So that's fine. We have a theoretical development which indicates that light behaves as a wave. Do we have experimental evidence that particles behave as waves? Well, 1927, an experiment by Davison and Germer where they directed an electron beam at a nickel surface and looked at the beam that was scattered and reflected from that surface, and they saw interference effects. You may recall interference effects correspond to alternating patterns of bright, dark, in that interference. So we do see an interference effect from the scattering of an electron beam that indicates that the electrons, which we think of as being particles, also can behave as waves. And again, here is just demonstration of this double slit experiment that we have talked about earlier when we talked about light, and we get these alternating patterns of bright, dark, etc. This classic interference, which is indicative of wave-like behavior. So now we've got a situation where you have electrons that seem to be behaving as waves under certain conditions. This actually raised an important question about the nature of reality. How can things behave as both waves and particles? How can light behave as a wave but also behave as a particle? How can particles behave as waves? What if we did a double slit experiment where we took an electron gun and fired just one electron at a time through this double slit apparatus and looked at what happened after it passed through the double slit and hit a screen of some sort to generate a flash of light. So this was the experiment that was carried out, and this is after 10 electrons. You may not be able to see this very well, but there are little bright spots here that indicate where the electrons hit the screen and set off a flash of light. So we're just going to go ahead and remember this is one electron at a time going through. After 100 electrons we have this pattern. After 3,000 electrons we have another pattern. You might be seeing something develop here. After 20,000 electrons we have a pattern, and after 70,000 electrons it's very, very clear that what we have is an interference pattern with bright, dark, bright, dark. So here we're seeing again that the electrons are behaving as waves, but here's the quandary. This interference effect, normally we think about the interference effect as being two waves interfering in a way that they reinforce each other, which gives us the bright areas, or they cancel each other out, which gives us the dark areas. Well, what's going on here if we're only doing one electron at a time? How is it possible with one electron at a time? What's it interfering with? You know, here if we look at 10 electrons, it seems to be kind of a random scattering on the screen. So how does this electron here know that after 70,000, where to go, so that after 70,000 electrons we've got an interference pattern? What's it interfering with? This is a real mystery, and a mystery of quantum mechanics that indicates some really strangeness in terms of our perspectives on reality and what that means. And I'm just going to leave that there for now for you to contemplate, but it does indicate how strange this stuff can be. So let's move on now and look at atomic spectra, because that's really what we're going to focus on here. We know that if we take this emission from a discharged lamp here and we pass it through a spectrometer, we get a series of spectral lines, discrete lines, not continuous lines. So why is it that we get these discrete lines where I might have a bright spot here, but there's nothing, it's just dark? Why is it not continuous? And that was something that really concerned scientists at the beginning of the 20th century. What's going on here? How can we explain this? We have no explanation for it. If we look specifically at hydrogen, for example, we'll see that hydrogen has 4 lines, although one of them is very dim and actually very, very difficult to see under normal circumstances. But we see a red line here at a wavelength of 656.3 nanometers. Then there's kind of a greenish green kind of line there at 486, and then there is this blue. We're getting into the blue-violet region over here on the left side of our diagram. So what's going on here that would explain these discrete lines, emission lines? Well, the explanation that we're going to be talking about has to deal with what's called energy levels. Where the atom itself, and this is hydrogen we're talking about, so hydrogen has energy levels, and we've numbered these energy levels 2, 3, in this diagram 2 and above. Why are we not using 1? Well, in the next slide we'll see what we mean by that. So as we're going up, we're increasing energy as we go up, okay? So we have these higher energy levels, and they are discrete, and we're just numbering them with integers here as we go up. Now, the colors here actually are important because they do match up the spectrum. And so what we're saying is this red light line here corresponds to what happens when a hydrogen atom, an electron in the n equal 3 state in level 3 drops down to n equal 2. And when it does that, because the electron loses energy, where's that energy going? It's being emitted in the form of light. Okay? And then the green line goes from electron going from level 4 down to level 2. The blue line is level 5 to level 2. The purple line, the violet line, is level 6 to level 2. All right, and so you'll notice the progression here. As we go, for example, from 3 to 2, the energy lost is less than the energy of going from 4 to 2. So this is more energy lost. So that means that the light energy is greater. So the photon, and remember calling these photons, the photon of light emitted from the 4 to 2 emission is higher in energy. We'll call that E4 for the photon, is higher in energy than what's emitted, the photon that's emitted when it goes from 3 to 2. Okay? And so one of the things that we note then is, because if we go back to the energy of photons, from the previous slide we had these equations, and what we'll note is that the photon going from 4 to 2 is greater in energy than that going from 3 to 2. And that means if we look at the frequency of the light, the photon that's emitted, the frequency of 4 to 2 is greater than the frequency of 3 to 2. Okay? And then, let me erase this here so we get... And then if we look at the wavelength, because it's inversely proportional, the wavelength from 4 to 2 is less than the wavelength from 3 to 2. And that's indeed what we see on the spectrum here. All right. What we're seeing on the spectrum is that as we go from high wavelength to low wavelength, we're increasing energy. So the energy is increasing from right to left here. So the red line is lower in energy than the green line, which is lower in energy than the blue line, which is lower in energy than the purple line. Shorter wavelengths are higher energy, photons. That's important to remember, particularly when we start getting into the ultraviolet region of the spectrum and start talking about ultraviolet photons. Those are even shorter wavelengths, and they do have higher energy. All right, so that's what we're talking about here. When the atom and the electron is emitting light, that corresponds to a situation where it's going from a higher energy level to a lower energy level. Okay? And the energy of the photon that's emitted is equal to the energy that's lost when the electron goes from a higher level to a lower level. And the shorter the wavelength of the photon, the greater its energy. Okay, so there is an equation that's called the Rydberg equation that will fit the observations. And this is the basic Rydberg equation that we've got. This is the reciprocal of the wavelength. There's a constant. This is called the Rydberg constant. And multiplied by this expression here, where N2 in this expression is going to be the higher of the energy level. So, for example, for the red line, all right, N2 for that red line is equal to 3. All right, and you'll notice it's squared. So this is an equation that actually fits the data, that explains it. What's actually going on then in terms of the atom, we know that there are energy levels. So, but what is the structure of the atom that leads to that? Well, the Bohr model, which we know is incorrect because electrons don't travel in discrete orbits. We've talked about that before. But the Bohr model was the first very simple model that was used to explain this. And basically each of these energy levels labeled N, 1, 2, 3, 4, and 5, etc., correspond to discrete orbits. So the Bohr model of the atom had the electrons orbiting in discrete orbits, specific orbits. So an electron could orbit here and could orbit here, but no place in the middle. And so, for example, again, just looking at the previous slide, so this is orbit 3, right there. This is orbit 3. So the red line came about when it went from orbit 3 to orbit 2. Okay, and the emission of light corresponded to that drop from level 3 to level 2, and in the Bohr model that means going from orbit 3 to orbit 2. And again, we know this is not a correct description of the electronic structure of the atom, because electrons don't orbit in discrete orbits. We now know that we quantum mechanics tells us that we have probability clouds that predict where the electron might be, but we don't have discrete orbits associated with that. So just a summary here. This is the Rydberg equation in general, all right, where there's a transition between two levels that are labeled by a number, an integer. And this R sub h is the Rydberg constant. 1 over lambda is the reciprocal of the wavelength, and we know it works actually for hydrogen only. And that's the thing, is it's a nice little equation that works for hydrogen, and in reality also works for anything that just has one electron. So it will also work, for example, for helium plus, which has one electron, but it doesn't work for anything else. So there you have that. And so in the case of the lines that we observe, visible lines that we observe, then the Rydberg equation, it turns out, can be reduced to this particular equation where all of the visible lines end up with the electron being in level 2, not level 1. And so if I just go back a little bit to the previous slide, let me just mention that the lines that go to level 1, which are indicated by this, and they're actually called the Lyman series, these are ultraviolet lines. So we don't see those because we can't see ultraviolet light, but these, the cascade of lines that leads to the electron being in level 1, the lowest energy level, actually results in the emission of ultraviolet light. The visible light emission always ends in level 2. That's kind of an explanation of what's going on there. So we're going to go with that and these specific equations that describe this, and we're going to look at some data and see if we can't actually use our data to determine the Rydberg constant and compare that to the experimental value that's been measured. So this is a brief discussion about this. Just let me know if you have any questions.